All right, let's get started. So today is about, I guess, two things you know well: connectivity and electricity. I don't really know what electricity is, but I've been around it for a while. So, hey, okay. So last time was our first kind of lecture in this segment, which has a little more linear algebra involved, talking about random walks and things like this. So it's might be a bit of a learning curve from a new language to get started, but hopefully as we practice, we'll get more familiar, more intuitive. Okay, so today we're just talking about connectivity, which you've all seen in an algorithms class. You just have a graph and two vertices, and you want to know if S can get to T. Okay, so for those who haven't taken my class before, because otherwise you'd know the answer to this puzzle, or presumably if you attended. Uh, so here's a connectivity problem. So it's a maze. Okay. I don't know if you can read the instructions, but you start at there's cats. Okay. Some cats are looking at you. You can see their eyes, and some cats aren't. You can't see their eyes. Okay. And your goal is to get from that starting yellow cat to the ending white cat. Okay. And you're allowed to, you have to go from like one cat to overlapping cat. They have to be touching each other. Okay. And you have to go from front to back to front to back to front to back to front to back. Okay. So there's some kind of implicit graph here. All right. So the question is, can start get can the starting cat, can you get from the starting cat to the goal cat? No. Adrian says no. Okay. Well, we'll wait for the second person to consider the maze. I got one more no. There's plenty of no's. Corbett thinks yes. Okay. Defiant. Or think kind of, give a little more time. I'm seeing a lot of no's. Maybe we'll take a vote. Let me not move it. Okay. So you can either say, yes, the starting cat can reach the end cat. Again, you're going from cat facing to not facing to facing to not facing. They have to be adjacent. Okay, trying to get from start to goal. Okay, so we're gonna take a vote. Who's not voting? Okay, 1, 2, 3, 4, 5, 6. Okay. Okay. I saw a lot of no's, so I'll do that first. Who thinks there's no way to get from start to end? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And then who thinks there is a way to get from start to finish? 1, 2, 3, 4, 5, 5. Okay. So we got 3 liars. Okay. Well, most of you said no. How did you conclude no, or how far did you get before you're like, yeah, it's impossible? What did you see? Okay, so you started from the back, so you went like this, and then maybe you can go like this and you get stuck or something. Yeah, okay. So from the back, yeah, anyone else on the no side have anything to offer? Okay. Who said yes? Hasn't seen this puzzle before. All right, Adrian, you tell me what. I'll start a start. You tell me what to do. So, oh, you said no. Okay. Anyone find a way? Okay, so maybe a lot of you guys like went like this. You probably got up to like this point and you got stuck or something. Now what? Anyone see a blue cat? You go like that. Okay. And you go like that. Yeah. Okay, so there's a blue cat right in the middle. Yeah. So this is why duality is important, right? You should always look at the opposite side of the coin. Okay, so the answer is yes. Okay. You can go feel dumb on your own time. Okay, so you probably learned breadth first search, depth first search to do problems like this. And I think the key feature of these algorithms, in fact, the breadth or depth doesn't really matter. All that really matters is you mark where you visited. Okay, and if you mark wherever you visit, you won't go through the same vertex twice, and you'll get this kind of linear time algorithm. Okay, you also get a linear space algorithm because you're putting a mark on every vertex. Okay, that seems, of course, very natural. But you might ask, can you do better than linear space? Okay, so all right, so you have lots of choices here. So you know you can do linear space. So we'll do a vote. So but everyone better vote yes on that. Okay, but then we're going to start raising the stakes. Can you do polylogarithmic space? Can you do just logarithmic space? Logarithmic space is probably as best you can do because, like, if the vertices are numbered 1 through n, that's just remembering the name of one vertex. Okay, and then can you do log n space deterministically? Okay, so so who's not voting? Um, yeah, maybe not even necessarily polynomial time. Although I should note if it runs in logarithmic space, it's definitely going to run in. Well, I guess maybe it depends. Anyway, don't worry too much about. Yeah, let's go with. Well, okay. There's a little bit of awkwardness, but still, polynomial or kind of polynomial time. Better than exponential time. Let's just. Okay. All right. Okay. So, anyone not voting? Okay, good. Okay, who thinks you can do linear space? Okay, so that's incredible. We have a good 96%. Who doesn't think we can do linear space? Okay, 4% liars. All right, who thinks we can get some polylogarithmic space? Okay, that's like almost the same 96%. Does anyone think you can't get polylogarithmic space? Did you vote twice? Oh, okay. All right. Okay, now who thinks you can even get logarithmic space? Okay, so it's going down a little. And who now doesn't think you can get logarithmic space? Okay, and then maybe the most extreme is logarithmic and deterministic. Who thinks you can do that? Okay, and then who doesn't? Okay, okay, all right, okay. So at least it makes sense. Like it, yeah. Um, okay. So in fact, well, okay, BFS DFS is in your space. Anyone taking complexity or have taken complexity? Yeah, complexity theory. Uh, did you confront this polylog space question in complexity? Do you remember much about it? What do you remember about it? A little. All right. Does Savage's theorem ring a bell? So it's a divide and conquer algorithm. So what you do is you try to guess the middle vertex, and then you say, can I get to the middle vertex in n over 2 and the side vertex n over 2? I mean, the remaining half from the middle to the end in n over 2 is going to keep recursing. It's not a very fast algorithm. It's quasi-polynomial time. That's why Wilber's question is a little awkward for this. But as far as space goes, you only have to worry about like one recursive stack. So you just guess, recurse, and you only go down log n levels. Okay, so you're only going down log n levels each time you remember the name of a vertex. That's another log n, so you get log square in space. Okay, so it says divide and conquer, but it's quasi-polynomial time. Okay. Log n to the log n. Or n to the log n. N to the log n. Okay. Today we're going to show that you can do it in logarithmic space, but randomly. Okay. And then most unbelievably, in a few lectures, we'll be able to show how to do it deterministically with logarithmically many bits. So you're just basically remembering a few numbers. Okay, so that's one of the more fantastic results we'll cover. Uh, but we'll only do that maybe in like a week. Okay, I don't know. We'll find out. All right. So, okay, so all these questions actually turn out to be yes. In general, there's a okay, what would be a very nice open question though? All of this is for undirected graphs. We don't know about directed graphs. Actually, Savage's theorem works for directed graphs, but we don't know for undirected graphs you can do logarithmic space. Okay, so this is like maybe the biggest question in this kind of space complexity area. Okay, good. Okay, so we're going to talk about a bunch of interesting stuff. All right, does anyone want to guess the algorithm? The randomized algorithm. You won't be able to guess the deterministic one. The randomized algorithm that runs in logarithmic space and I don't know, works with high probability, runs in polynomial time. Yeah. Uh-huh. Yeah, at some level, I guess what else can you even do? So, okay, we're going to start at some vertex. I'm going to randomly walk for mn steps, and if I reach t, then I return true. Okay, that'll work with constant probability, so we'll repeat log n times. Okay. All right, so you'll succeed with high probability, assuming steps A, B, C work with constant probability. Okay, and I guess for us, the real question we'll be asking is, if I started randomly walking from S, what's an upper bound on how many random steps I need to take to get to T? I mean, it's going to always be finite because there's some path that gets to T, as long as the graph is connected. But trying to get this upper bound that's polynomial, that's going to take more effort. Yeah. All right, so that's the very simple algorithm. And at some level of this, I don't know if that makes a deterministic thing even more dramatic because this seems like such a random algorithm. Okay, but this has probably been known for a gazillion years. Yeah. Okay. So why is it log in space? Anyone want to? What does the algorithm need to keep track of? Yeah. The current vertex. Maybe one more thing. Yeah, a counter. How many steps you've taken because you want to stop after mn. So just two counters, log in each. Okay. All right. So, so this is really just a lecture. Yeah. That would also be okay. That would also be okay. Yeah. At some level, you can even see it just from this. I mean, if any arbitrary ST should be enough, then wherever you find yourself at the end of MN, your first MN, another MNT step should hopefully get you to T. Yeah. Okay. Good. Okay. So, all right. So here's maybe some two terms that if you open up some book on random walks, you'll quickly run into. All right. Hitting time is the expected number of steps that a random walk starting from S will reach T. Okay. How long it takes. A cover time is expected number of steps until a random walk from S visits every vertex in the graph. All right, so okay, so what we're really going to kind of focus on today is that if the graph is connected, then the cover time is at most m times n minus 1. Okay, so in fact, you should be able to, in expectation, visit all the vertices. Or, okay, that's not quite the right use of expectation, but anyway. But okay? Okay. All right. Good. Good. Okay, so that's our goal, to try to analyze the cover time. And okay, but we're going to do so in like a completely unusual fashion. Okay, so we're going to take quite the detour and somehow come back to this question of random walks. So That is a Have you heard of Money Python? Uh, okay, well, I don't know how long we should pause the lecture to discuss Money Python. It was a comedy sketch show from like the 60s, 70s, 60s, I think. Anyone know? Huh? What year did Money Python run? 69. Naturally. 69 to 83 was the original premise. Okay. Yeah, and also things like the Holy Grail and the Life of Brian and various amazing things. Uh, but their skits were like basically schizophrenic. Like they would just do one thing and then do something completely different. And this was one of their kind of interludes. Okay. Uh, right. Okay. So we're going to talk about electrical networks. Okay. So we're going to talk a little bit about electricity. Okay. So if I put a battery or Pikachu who kind of injected one kind of unit of electrical flow on one end and tried to remove one unit of electrical flow coming out of the other. Okay. Electricity will take something called the path of least resistance. Now, the question is, what is the path of least resistance, or what does it define? Or what defines it, I guess? What characterizes it? Like for us, what would be the most natural path of least resistance? Usually when we do algorithms, yeah. Shortest path. And the most natural thing, I think, from our typical background is to take the shortest path. Yeah, that is probably what we think of as path of least resistance. But that's not actually what electricity is trying to optimize. Anyone know? I think we have some electrical engineers here, or aspiring. Okay. I don't know what any of those words mean. Okay, so the path of least resistance is going to send. So if you're just sending one unit of flow, so if you have edge weights, they call them resistances. Okay, and the electrical flow is going to minimize a sum of squares instead of just a sum of like lengths. Okay, so you need to send one unit of flow from S to T, and you're going to minimize this weighted sum of squares, where the edge weights are kind of become these coefficients. So if it's unweighted, all the REs are equal to 1. It's just the sum of FE squared. Okay, so it's flow, but you're minimizing a sum of squares. So that means if you're trying to get from S to T with minimum electrical energy, that would be the sum of squares. And I could have put like 1/2 here or something, but it doesn't matter. You actually want to spread out the flow, right? Because 1 squared is 1, but 0.5 squared is 0.25, and 0.1 squared is 0.01 and stuff, right? So to really get the squaring to kick in, you actually want to disperse the flow from S to T. This is not the actual flow of this network. I have no idea what it would actually be, but this is, you get some sense. This is actually a flow though, hopefully. Okay. All right, so that's the electrical flow. Now, what we want to kind of treat this algebraically, so we just need to do a little bit of setup to do some notation. So you start with an undirected graph, but I want to talk about like a flow vector sending some flow that way or some flow this way along an edge. So what I'm going to do is I'm going to orient the edges arbitrarily, just fix any orientation. Okay? And then I'll have a vector that's kind of indexed by, say the underlying undirected edge. But if FE is greater than 0, that's going to be sort of flow in the direction of the orientation. And if FE is less than 0, that'll be flow in the opposite direction. Okay, so you fix some direction so that positive means with the direction, negative means against the direction. Okay? All right. So you're just picking some vector f, and you'll interpret positive, negative consistently, whatever you do, but it doesn't matter what you do. Okay, so now what I want to point out is your flow, it needs to conserve flow. For S, it needs to kind of take one unit of flow out. And for T, it needs to put one unit of flow in. Everywhere else, what goes in is what goes out. right? So suppose I made some function b that takes your flow as like a vector, and it just calculates for each vector vertex what's the net flow. Okay, so if this is your vertex and you have some kind of orientation, and you have values like 2 and 1 and 1 and -2 and 3 and 1 and 2, I guess, all that would add up to, oh, this is going to be very confusing. So you're going to get, so as far as the amount of flow that's going out of V, as far as the amount of flow that's going out of V, -2, -2, -1, so -5. No, got it backwards. -3 at this point, -5, -7, 4, 5, no, -4, -3. What's the net flow going out of this vertex? Neg we should at least get it right up to a sign. Okay, so we'll call that alpha. And the point though is that it's a linear function of f, right? If I took two flows and I added them together, all the net flows would add up or subtract or scale and things like this. So I don't really care what it is. The point is that it's a linear function. It has some matrix. Okay, that matrix is going to be like, you know, the input side is edges. So it'll be one column for every edge. The output side is vertex. And then it's going to be like ones or negative ones based on the orientation. You know, that flow, is it adding to the net flow or is it subtracting? Okay. And so what we want is we want to choose some vector f that's just assigning values to all the edges. We interpret that as flow, but it should be sending one unit of flow out of S and one unit of flow into T. Okay. But the only point I really want to make is it's just a linear constraint, which from a math point of view is like the simplest kind of thing, non-trivial thing. Okay, so good. So at some level, the electrical flow is just a relatively simple convex minimization problem, right? Like minimizing sum of squares, that's sort of like your canonical convex function, but it's subject to flow constraints. Okay, and the electrical flow is just the optimum solution of this kind of basic problem. Okay, so I think the natural thing to do when you face a problem like this is, huh? We're going to just study what the optimality conditions are, as you often do in convex minimization. Okay. Okay, so let's do that. Okay, so what we're going to do is we're just going to look at like what it means to be the optimum solution. We're going to pull out something called Ohm's law. Okay. Which I otherwise don't really know what it means. I just know the math. Okay, so maybe somebody here knows. F is the electrical flow, so it kind of solves this optimization problem. So assume F already routes D. Okay, so I'm just worried about the minimizing the electrical energy at this point. So F is the optimum flow or electrical flow. If and only if, does anyone know? I think that's more like it is a flow. The electrical flow is a comment about the objective, minimizing the sum of squares. I was just wondering if anyone here is like really into electricity. Guess not. Okay, so much for electrical engineering. Okay, so if and only if there's some vertex potentials, which might be called voltage sometimes, but I'm not 100% sure. There's some kind of assignment of values to every vertex. So the flow has the following form. The flow on an edge E is equal to the potential at the end, the tail minus the head minus the tail divided by the resistance. So at some level, F is the electrical flow if and only if there exists some kind of vertex potentials that sort of induce the flow. Okay, and then in turn, those potentials have their own meaning in the study of this stuff in physics. Okay. All right. So how do we prove this? Yeah, I think they're called voltages. That doesn't tell you what they mean. I'm not the right guy to go ask ChatGPT. Okay. Yeah. Yeah. So these voltages are translation invariant, right? I can take P and shift everything up, shift everything down. It won't matter. Well, I think the scale is sort of fixed by a fixed D. So D is fixed here. I could double D and then the flow will double and the potentials will double and things like this. So it's scale invariant in some sense. If I doubled everything, I mean, if I doubled one thing, everything else doubles. But it is the P's are translation invariant. It doesn't matter where you start. Okay. All right. So let's do maybe the one direction first. So let F be the electrical flow. Okay. It's the optimum solution of a convex minimization problem. Okay. So like you're doing convex minimization. What should you look at? Like what's one kind of object we're obsessed with when we do convex minimization? Yeah. It's locally optimum. Yeah. How do you certify that? Gradient. Let's look at the gradient. Okay. And let's do something maybe a little. So I should mention I used to prove this a little differently and more abstractly. Today we're going to do a different, more combinatorial proof. But let's look at the gradient. And let's think about the graph with edge lengths given by the gradient. Okay. This is really like a bidirected graph because you have gradients kind of in both directions, edge lengths in both directions. Okay. But if I look at like especially if I put 1/2 there, but 1/2 the sum of E RE squared. Okay. The gradient for each edge is REFE. If I had the 1/2 there. If I don't, okay, there should be a factor 2 there, but it doesn't really matter. Okay. So I'm going to look at the gradient, and I'm going to think about the graph as the corresponding edge length. So this is a bidirected graph. Like the gradients will be kind of opposite in opposite directions, or negated. Okay. All right. Now, okay, so I claim that if F is the electrical flow, in this graph, there's no negative cycles. Why? So I looked at the gradient of kind of my electrical energy, and I turned that into edge lengths. And I'm saying, okay, if this is really the optimum electrical flow, there's no negative cycles in this graph. Yeah, because it's convex. I would say, convexity is in the air, but I wouldn't say that's a full solution. Yeah. So in a cycle, what goes in is what goes out. Yeah. Uh-huh. The potentials don't exist yet. We're trying to show that potentials exist. It's like there's this arrow. So we're on the left, and we're trying to get to the right. But hold the thought for the other direction. Yeah. Okay, so you have some cycle, right? Okay, so I have, some flow, and there's some cycle. If I push flow along this cycle, it's still routing the same overall demands. Like if this was a unit ST flow and I added some flow along this cycle, it's still a unit ST flow. So whatever the demands don't change, what I'm routing doesn't change. So I can always add cycles without changing anything, right? Now, if the total length of this cycle was strictly negative, think about what gradient means, right? It means if I infinitesimally add a little bit of flow along this cycle, it should go down at that rate, right? So if this was strictly negative, then I'll be able to add a tiny amount of flow along this cycle and push down the objective because you're going down. That's what the gradient is, right? In this direction, this is how much it changes. So this would be a direction that doesn't violate any constraints, but pushes the objective down if it was a negative cycle. But F is optimum. Okay. All right, so that's okay. That's that. It just says what, at some level, what does the gradient mean? And maybe it's sort of weird to see that show up as edge lengths and stuff and make some of these connections to graph stuff. But ultimately, what does the gradient mean? Okay, good. So you have no negative cycles with respect to these edge lengths. Anyone want to guess what to define the potentials as? Yeah, shortest path from where? Ah, okay, I could do it from S if B was an ST flow. What about if it was general? Yeah, arbitrary is probably okay. I went with this kind of thing. I think because I've been doing so many shortest path algorithms. But for every vertex, just pick your minimum S and then do the shortest path distance from S to V. Right? What does that remind you of? Johnson's algorithm, right? For all pair shortest paths. Okay. All right, so let's look at these potentials. I want to show that this is going to induce the flow, the electrical flow. Okay. So just the potentials are some shortest path stuff relative to the gradient. This is crazy, right? All right. Okay, so let's see. All right. What can I say about PV minus PU? PV is the shortest path to V, shortest distance to V. PU is the shortest distance to U. Yeah. Oh, maybe for an edge UV. Sorry, I should have written that. Okay, so let's say I want to do this, right? So let's fix an edge A is equal to UV. Okay. Uh, so even more refined than the distance from U to V. Yeah, yeah. So the length, which is, yeah. And then Y, triangle inequality. Okay. All right, now let's look at the opposite direction. You have the same thing. PU minus PV is less than or equal to LVU. Same triangle inequality, nothing different. Okay, now what? Remember, our goal is to try to get eventually to something like this, which for us is really saying PV minus PU is equal to LE. They're symmetric. LUV is not quite equal to LVU, but you're on, okay, why is LUV equal to negative LVU? Because it's just the opposite flow. It's supposed to just be the, ah, okay, right? Because flow in one direction is negative flow in the opposite direction. Okay. Now, when you put everything together, what do you get? Okay, you put everything together, you're going to get PV minus PU is equal to the edge lengths. Okay, and that's what we wanted. So the potentials are somehow coming out as shortest paths with respect to the gradient. Pretty cool. Okay. All right. Any questions about that direction? You and your pump fakes. Okay. All right. Now let's go in the opposite direction. So now I have some flow that's induced by vertex potentials, okay? Or, they agree with some vertex potentials or something. And I want to show its optimum. So one thing I can do is I can take any other flow and try to show it's better than that flow, or at least as good as that flow, right? Okay, so if I have my flow F and I have another flow G, they're both routing D. Maybe that's an ST flow or something. What can I say about F minus G? What is it routing? Huh? It's the flow in the sense that everything's getting conserved, but what's it routing? What would D look like for F minus G? A zero, because they both route D, but they're subtracting, right? So if you have like two different ST paths and you subtract it, you get a cycle, right? And that's sending zero flow everywhere. But there could be flow on the edges. It's just that there's no real source in sync anymore. Okay. So does anyone know what that's called? There's a big word for it. It's called circulation. Okay. So that means you have net flow zero everywhere. And the circulation can always be broken down into like a sum of cycles. You find one cycle, you rip it out. Find another cycle, you rip it out. Okay. All right. So now let's again look at those same edge lengths. That's sort of the gradient with respect to F, although this time you also know that F is induced by vertex potentials. Okay, now we're going in that direction. All right, so now for a cycle C, what is the length of the cycle in Y? Zero, and Y? That's right. So once you're induced by potentials, then everything's going to cancel out. You're going to get this telescoping series all the way around the cycle. So it's always equal to zero as long as it's induced by potentials like that. Okay, good. All right, so now, okay, so for those who have done maybe some convex analysis before, what's a typical way? Like you have one point and one point, you want to show one point's better than the other point. Okay, so you want to invoke something like convexity. Okay, so you know that I'll write kind of the script E of F to be this energy function. Maybe there should have been a 1/2 there. Okay, but convexity says so. E is a convex function of F, right? It's just a sum of squares. So convexity will say that like the energy of this flow is at least the energy of F plus something, something, something. So what does a convex function look like? You're here. Yeah, the gradient, right? So if this is F and this is G, this is the value of F, and then I kind of interpolate along the gradient, right? It'll always be underneath the curve. Okay, so that's the usual thing about convexity. But now what? Okay, we can substitute in, right? Okay. All right, so our gradient is L, and G minus F we already discussed as circulation. So now what? It's zero Y? Yeah, and yeah, how do I connect circulation to cycles? A circulation is always a sum of cycles, right? So you have all these things where, so you can find one cycle in your circulation and then rip out as much of it as possible, and now one edge is gone from the circulation because you're bottlenecked on some edge. And you can gradually keep ripping out cycles from a circulation until there's nothing left. So every circulation could be written as some kind of combination of cycles, and you get zero on every cycle. Okay. So you get that it's at least E of F. Okay. All right. So okay. So this is very nice. Yeah. As a dot product or inner product. We did, but it was like a few minutes ago. Yeah, if you're a goldfish, then okay. Yeah, so that was the first direction was just showing their exist potentials. There is some similarity because they're both doing this gradient trick with edge lengths. And they're all kind of based on cycles and paths and things like this. But yeah, that's how we got potentials. The potentials arose as shortest path with respect to the gradient. And on the flip side, if I interpret the gradient as edge lengths, then I can say something about cycles once they're induced about by by potentials, and then I can reason very easily about moving along a gradient from one flow to another. Yeah, for every single edge. One flow is sending 5 this way, the other one's sending 2. The difference left will be 3. Yeah, so just as vectors. Everything's linear, so like things kind of go through nicely. Okay, any questions? Okay, so that's Ohm's law, I guess. Uh, and yeah, but at some level, it's just it's not. It's just like a consequence of the setup. Okay. Okay, so um, the optimum value of the solution, the actual energy that's attained by the electrical flow, I guess, is called the effective resistance of of these demands. Okay, I don't know how they come up with these names. Okay, all right. Let me switch gears again. Introduce yet another object. We're going to kind of do a lot of different stuff today. All right. Next thing I want to do is introduce something called the graph Laplacian. That would be the matrix form, but it's a little bit hard to understand like that. So, okay, let me go through slowly. So the Laplacian is going to be indexed by vertices on both sides, square matrix V by V. Okay, so at some level, it's going to take in something that looks like vertex potentials or something on each side, assigning values to all the vertices. If I just start expanding this thing out, yeah, I feel like I didn't give the friendliest definition to start with, but we'll get a better one equivalently. This is just doing nothing too exciting. But okay, so B was the thing that took flows and outputted the net at each vertex. And if you transpose it, right, and you're looking at a particular edge, you're going to get 1 from one vertex and -1 from the other one, based on how the edge is oriented. Okay. So okay, so you end up getting something. I'm missing a squared. Okay, so maybe I can draw a picture of B. So B is trying to. So if I have an arc from UV and I look at the U column and the V column, and I'm doing the net flow that goes. Oh, did I get that backwards? I got it backwards. Okay. So B, remember, was uh, trying to map uh, flows to the net flow going out of a vertex. Okay. So if I'm looking at an edge UV and how much flow it sends out of V, if I put 1 unit of flow along UV, it'll be -1. And if I look at U, if I send 1 unit of flow along UV, it'll send 1 unit of flow out of U. So that'll be 1, and it'll be 0 everywhere else. Okay. So when I start looking at the transpose, so the X is a bunch of values on the vertices, right? And for that particular edge, it's going to be XU minus XV, or maybe XV minus XU. Doesn't matter because it's squared. Okay. So what the Laplacian does is it takes a bunch of vertex potentials. Like the 1 over resistance is a little bit mysterious. That's actually called the conductance of electrical edge, I guess. But it's sort of taking the square difference across every edge. Okay. All right. So why is that useful? I don't know. We're going to be talking about the Laplacian a lot. in like the next week or so. Yeah, so x is just some vector over the vertices. I could, sure. I mean, I feel like potential is already a word where it's like I don't know what else to call it, so I'll call it a yeah. Oh, I always forget this. R will be the diagonal matrix of resistances. Okay, so the square diagonal matrix was the resistance of each edge. Okay, E by E. All right. Okay, so that's sort of a crazy. I mean, at that point, it just looks kind of numerical. Let me give some interpretation. This will make a little more sense. Okay, so what I want to show is that the Laplacian actually does say some useful things about the graph. And here's a simple example. Okay, I'm going to try to show that it encodes the value of every cut in the graph. Okay, so in particular, we're looking at the graph for the edge weights that are reciprocals of the resistances. Okay, and if I do something like kind of pick some vertex S and I put 1/2 for everybody in the set and -1/2 for everyone outside the set, and I repeat the same calculations from before, okay, you're going to get something like this. Here's the edge weight, but you'll get 1/2 minus 1/2 for all the edges that are in the cut. Okay, we're dropping all the edges that are stuck on one side in S or in not S, right? So if you're looking at an edge that where both endpoints were in S, you get 1/2 minus 1/2. If you're looking at an edge where both endpoints were outside S, you get -1/2 minus -1/2. So they both zero out. So the only edges where there's a difference are the edges going across the cut. Right? So Laplacian is giving you some kind of sum of squares, sum of square differences over every edge in the graph. But if you have that, then you, for example, can recover all the edge cuts, which is very useful, right? That means you also know something about all the ST flows and all these things, right? Because cuts give you a lot. Okay. In fact, yeah, we'll also be looking at a sparsest cut algorithm based on some of this in maybe next Thursday or something. Okay. Oh, okay. Yeah. So you get the weight of the cut. All right. So, all right, not to like put more terminology on you, but here's maybe the next thing we'll do. All right, so the effective resistance, that's just whatever is the optimum value. Before I presented it as some kind of like minimizing sum of squares subject to some flow constraints. There's a constrained optimization problem. So this will be a different characterization. It says, look, the electrical potentials for a particular set of demands are always going to satisfy LP is equal to D. Okay, and an electrical energy will always be D comma L minus 1D. Okay, so somehow everything is just going to like coincide nicely. Okay, I feel like I don't have a very intuitive proof for this. I think we're just going to do the calculations. So maybe I'll just try to make it mildly expedient. Okay, okay, so I think this is actually not so bad. So some of it is just kind of keeping in mind what L is and expanding things out. Okay, so when we showed that REFE is equal to PV minus PU. Okay, that should map to saying that RF is equal to B transpose P. Okay, so now when I look at something like LP and I just start plugging in BR minus 1, B transpose P. Okay, and now how do I start plugging in F? You substitute R. Okay, so we can do that. BR minus 1 RF. These R's cancel out. And then what does BF give you? Best friend. It gives you D, right? So FB is supposed to take a flow and tell you what it's routing. Okay, so you get LP is equal to D. That also means that P is always a solution to this, linear system. You can solve LP is equal to D, you can solve for P, then you're done. All right, that's one reason why Laplacian solvers are very important. Okay, as far as the electrical energy part, I think this is just a bunch of plugging in. So FRF, and we just apply Ohm's law a bunch of times. So you're going to get something like R minus 1 B transpose P, because F is equal to R minus 1 B transpose P. Then you get R, and then you again get R minus 1 B transpose P. Okay? And that, when you start like canceling these guys out and you start transposing things over, you're going to get something like P LP, okay? Which if you really want, you can then rewrite further as something like LP comma L minus 1 LP, okay? Just like including L's and L minus 1 terms. And then you'll get this D L minus 1 D, okay? So that means if you could take a graph and you can invert L, then you can take any demands and just immediately pump out the electrical energy. You could also, get the potentials, because the L minus 1D is the potential. And then you can get that and just get the flow. Okay, so what was originally, presented as a sum of squares problem. You might ask, like, how would I solve this electrical energy problem? When you start looking at the first order condition, you get all these identities, because the first order conditions kind of remove a degree of freedom. Right? Optimality, this has to be equal, and then suddenly there's no choices to be made. And then you just get things like, oh, okay, the potential is always LP is equal to D. If I can invert L, then I get P. If I get P, I get the flow. Okay. So some level of first order conditions, once you start thinking in terms of P, you're actually looking at an unconstrained problem. Originally, electrical flow is like, oh, I imagine doing some like forward focusing crazy thing. I'm winding through the graph because I'm trying to satisfy these flow constraints, right? Some routing paths or something. But here, once you look at the first order condition, it actually makes the constraints evaporate, and you're left with an unconstrained problem. Yeah. All right, so there's all this kind of nice stuff. Some level, we're going to have to get back to the original random walk thing. Okay, but that was our kind of whatever discussion on electricity. Any questions about electricity that are like within the scope of? Okay, all right. Let's go back to random walks now and somehow try to make this bizarro connection. Okay. Or what we're originally trying to show is kind of incredible, right? You start randomly walking from S, and if you can get to T, you'll probably get there in a polynomial number of steps. And then somewhere in the middle, we talked about electricity for no reason for like half an hour. And somehow we're now go back to the miracle claim. Okay. All right. So hitting time, right? Expected number of steps until I get somewhere. Let's just kind of start modeling things recursively. So let's say I'm focusing on the hitting time to get to my destination T. Okay. We'll start simple. What would be ht of t comma t? How many steps do I need to get from t to t? 0. Okay. How can I model hut recursively? Remember, it's a random walk. So, okay, 1 plus, because you take one step and then? Yeah. Okay. So you take one step from u, assuming u is not t, right? And you choose one of your neighbors uniformly at random. And then from there, you take however many steps you need to get to t. So we divide 1 over degree u. It's an undirected graph, so the same as out degree. And then you're summing hxt over all the neighbors x. Okay, so kind of simple, model it recursively. Okay, let's see what comes next. All right, now things get a little more mysterious. All right, we're going to define vertex potentials using these hitting times to t. Okay, anyone want to guess? Square of ht. No, but at least you guessed. Okay, so it's going to be negative hu of t. Okay, I don't really know why, but we'll see how it works nicely. All right, and that induces some flow, right? Let f be the fuv is equal to pv minus pu. Okay, there's no resistances anymore. We're looking at unweighted graph. Okay, so that was supposed to be erased, but anyway, if I look at this here, right? HUT is equal to 1 plus thing. Let me plug in the PUs and PVs. Oh no, it wasn't supposed to be erased. Okay, so I get negative PU, that's HUT. 1 minus, because all the minuses here, I switched from X to V just to piss you off. Okay. All right, good. All right, so now if I rearrange this, okay, then what do I get? So I'm going to rearrange this. I'm going to kind of multiply everything by degree U, clear that denominator. And now I have sort of degree U copies of PU and then a bunch of PVs. Okay. So I can write on one side the sum of PV minus PU. That's the flow from U to V for every out neighbor V. Okay. And if I do rearrange, what would be on the right side of this? Degree of U. Yeah, so I think we multiply everything by degree of U, then we throw the sum from right to left. Okay. All right, so in other words, this flow that's induced by this potential, what is it routing? Almost. Okay. So what is it? So you have these potentials induced by this flow that's induced by these potentials, which somehow goes back to the hitting time, right? But what's it routing out of every vertex, and it's doing t a little bit differently. Well, here you said if I sum over all the edges leaving U and the flow, I get degree U. So you can think of each non-t as like a source because it's sending out degree U units of flow on net. Okay, so it's a degree U kind of source. So you have a bunch of sources. You can think of a super source attached to everything. And then how much goes into T? So M minus what? Because we don't have any analysis for T, but you can still deduce what T must be. Sum of degrees. Yeah, so another way to write that is, because if I sum up all the degree U's, I'll get 2M, right? I'll count every edge twice, except I left out degree T. Right, so basically all this flow that's going out of these sources have to go into T. That's how you get this. Okay. So you get some flow that looks like this, I guess. So all of these non-T who is T? Well, no, well, I think this should be a T. Let's make this a T. Okay. So all the non-T's are sources relative to the same value equal to the degree. And then I highly doubt I actually added them up. But T should be, the number of edges times 2. There's no way I drew 50 edges, so that can't quite be accurate. Okay, but you get the point.
Why is the battery connecting to like so many?
Well, because every vertex is a source. Yeah. Uh, that's the most explanation I can give. Like, some of them I'm allowed some artistic freedom. Okay, all right. Okay, so that's some kind of flow where you can interpret the hitting. So if you take a look back, at some level, it's just that this kind of recursive formula for HUT can be rearranged as something that looks like a flow. It's almost a coincidence. Maybe at some level I feel like it is. I don't have anything too deep to say about it. Just the ramifications. Yeah. Is it related to Markov chain? First what? I don't think I recognize the terminology. The first step? Well, so HUT right now does satisfy that we drew up a linear system, but not all linear systems are going to kind of have a structure that can be recast so nicely into flow. So that question is a little bit, it feels a little magical to me. Exactly why, but maybe I should think harder over the weekend. Okay. All right, so now I'm going to try to prove this. The hitting time from U to V plus the hitting time times V to U is 2m times the energy of a unit UV electrical flow, right? Which is just some insane claim, right? Because it's even equal, right? It's exact. Okay, so what is? Oh, there's nothing here. Any ideas? Okay. All right. So let's let P, but it be the potential defined by negative H, something the hitting times to U. And let Q be the potentials defined by hitting times to V, negated just like before. Okay. And let R be the difference of the two potentials. Yeah, so these are all vectors over the vertices. They're all vertex potentials. Okay. And then I'm going to let D be the unit UV flow demand. Okay. So if I look at the sum of these two, that's what we're trying to bound. I would just get negative PV minus QU if I did that correctly. Okay. And here, what I'm going to do, so what would PU be equal to? PU be equal to 0. Likewise, QV is also equal to 0. So I can write something like this. Okay, so I just added this. This is 0 and that's 0. Okay, because they're really hitting times to themselves. Okay, and that would give you RU minus RV. Okay, because you get PU minus QU, PV, QV minus PV. Okay, which for the unit demand, sending one unit flow from U to V, that'll be a 1 and a minus 1. Okay. All right. Stay with me for 9 more minutes. All right, now let's look at the corresponding flows. Okay. So G is, induced by P, so it's PV minus PU is how much flow gets sent on UV. H is induced by Q, and F will be induced by R, which will also be equal to G minus H because it's equal to P minus Q. I mean, it's induced by P minus Q. Okay. All right. So what is G routing? Well, let's go back to here, right? So G was G was the flow induced by these hitting times to U, right? So what did we find about this last time? Yeah, 2m. Okay. So this is routing, I guess, degree x out of all x not equal to u, and then everything else into U, right? And then likewise, what about H? H is going to route degree X out of all X not equal to V. And yes, everything else goes into L. So all else into U, all else into V. Okay. Now, what does F route? Okay, so maybe let's go through some cases. So what if X is not equal to U or V? It's going to be 0. Okay. Now, what about U? So it's going to send maybe 2m minus degree U into U, right? So let me just fill in the all else. Okay. So if I look at G minus H, what is it routing out of U or into U? Yeah, so it's going to send 2m into U. And then what about V? Also 2m, but it's going to go out because we're subtracting H. And plus they have to add up to 0. So 1 plus and 1 minus. Okay. So F is a 2m size flow from U to V. Okay. Oh no. Okay, let's hope this doesn't break. Okay, good. 2m from U to V. Yeah, okay, that's fine. Or is it V to U? V to U. I wrote U again. That's a little annoying, but that's okay. All right. That also means negative F will route from U to U to V, and it's the same electrical potential. Okay. All right. So now, what was that? What's going on? Oh no. No. Oh well. Okay. 2m V to U. All right. Okay. So we started before by saying HU plus HV is equal to like RV minus RU or something. And all right, so what is this thing equal to? So if we go back to some of these identities, actually, is that even necessary? Let's just see what happens. Okay. Okay. No. So we know that the electrical flow for D, because R routes D, right? R is potentials routing D, and R always induces the electrical flow. As soon as you come up with potentials that match the demands, that's the electrical flow. And this is your turning it into a flow. So B times, B is equal to BF, which is equal to B transpose R. Okay. And okay, but yeah, because F actually routes 2m units of flow. There is okay, I'm using R twice, but now we're looking at a graph with no resistances. So the big R became the identity. And then we started using a new R because I went PQR. Yeah, just to piss you off. Okay. All right. Keep them on their toes. All right. So we go like that. Let's see what happens next. Okay. So I'm just flipping a B over. B transpose R, B transpose R. And okay, so now what is this describing? Uh, yeah, it's the sum of squares. So this is the electrical energy of F. Okay, which also I could write as, I'm really interested in a unit flow from U to V or V to U or whatever. So I'm going to divide it by 2m, and then now suddenly I have a 2m on the outside. Okay, but this is the electrical flow, routing one unit of flow from U to V. So this is exactly the energy of a unit UV electrical flow times 2m. Okay, so somehow this Ohm's law, which is really first order conditions, just makes everything kind of magically work. Okay. All right. Okay, so that's this crazy claim. Okay, so we're making some progress for any pair of vertices, HU plus H plus HVU, the hitting time from one and the hitting time to the other direction is 2m times the unit electrical flow on this undirected graph between the endpoints. Okay, that's insane. Okay, good. Now, you might be able to guess this. I want to prove, finally, using that amazing, insane connection, that the cover time from a particular vertex is at most 2mn. Yeah, it's completely crazy. So far, you've somehow made a bizarro connection between electrical networks and hitting times. Okay? So the hitting time from U to V plus the hitting time going back is always at most 2m times the energy of a unit UV electrical flow. Somehow I'm going to translate that into a claim about the cover time. Now you want to visit all the vertices, yeah. Can you do a linear of expectation to the kth vertex you visit or something like this? Uh, uh, no, I mean, at some level, if you do next vertex, isn't it always one or something? Oh, you could have gone back. Yeah.
Is it like HUV plus HVUs? Like you have to go from U to V and then back to U, so you can just solve over all of it.
So okay, so there's an n there. So at some level, if I could like do if I can come up with like sort of n edges that lets me cover the whole graph, n UV pairs, that would be a start. So how can I come up with like n-ish edges to connect the whole graph? Spanning tree. Okay. So take any spanning tree and fix any traversal. So check this out. Boom. Okay. New iPad trick of the day. Okay. Okay, so fix any traversal of this spanning tree. Okay. And now how long does it take, to go from here to here? HUV for those endpoints UV. It might go all over the graph before it gets to here, but it'll get to there. And then how about there? Another HUV, another HUV. And a nice thing about this traversal is that you use each edge twice, once in each direction. So for each of these undirected edges, you'll get an HUV going down the tree and HVU coming back up. Okay. So for each one, you're going to pay, something based on the energy of the unit electrical flow between those endpoints. Okay. So I think that's all that's hidden down here. So total time looks something like summing over all the things HUV plus HVU. Okay, good. All right. But to make that thing useful, we need to be able to bound what's down here. Hope I don't blow it. Oh, okay. That's fine. Okay, so some sum of all these energies for every edge in the graph, right? Okay, but now we have to figure out how to bound the energy of a unit UV electrical flow. We need a hard upper bound that always works. Okay, 1. What is the 1?
Battery.
Well, but no, it's not. In fact, that's like the only answer you could have given that's wrong. What would be a electrical? I mean, a flow from U to V of energy 1. Path? How about an edge? Okay, that's some flow that gets you energy 1. The electrical flow is only going to do better. Okay, so it's at most 1 because you can just use that edge. Okay. Oh, we're doing fine. So now we start adding all this up. Each of those are 1, and then you get n. You know, probably more appropriately, n minus 1. Yeah. Okay. All right, so that is it. So somehow, by sort of this amazing connection between electrical flow and electrical networks and hitting times, okay? Somehow we took the hitting times and treated them as potentials and looked at the flow, and then voila. After learning a bit about electrical flows along the way, we were able to bound the cover time to 2m times n minus 1, right? That's just absolutely insane. Okay, so that's it for today. So we learned a lot. The Laplacian stuff is going to recur all next week. Yeah, question? Sorry?